Okay, good morning, everyone. Welcome to this session about parallel computing. So this is a very short session just to introduce the sessions that will come afterwards that are about parallel programming. The first thing I would like to show you is the agenda for today. So I will first give you some definitions and some concepts. I will not go deep into theory, just to make sure that we are speaking about the same concepts when we use the same words. Then I will give an overview, bird's view of the hardware that you can use for parallel computing. And just after that, I will show you the different programming models. And you will see some programming models this afternoon, some others on Wednesday. But here you will have the full list so that you can understand the big picture. And then I will spend most time talking about user tools. So tools that are readily available in a Linux distribution that will allow you to compute things in parallel without writing parallel software. So first, the general concepts. And the first slide is a question, which is why would we want to go parallel? There are mostly three reasons. The first one is when you have a problem, it takes too much time to solve it. You want to solve the same problem faster. That's what we refer to often as to speed up. You have a problem, you need to speed up the solution. Second option could be that you need to solve a larger problem than the one that currently fits on the computer that you are using, maybe your desktop or a workstation, and that is called scale-up. Or maybe you have a very large number of such problems that you need to solve. And so all of them cannot fit into one computer, even if only one of them does. And so this is what we refer to as to scale out. You will hear later on the strong scaling and weak scaling, and they are related respectively to speed up and scale up. Each reason has some challenges that we need to address when we want to go the scale-up or speed-up path. Whenever we need to parallelize, there are two things that we need to consider. The first one is a decomposition of the work. So some amount of work has to be done, and it has to be chopped, split into multiple pieces. And that involves distributing the instructions to the processors, so to the workers, and also distributing data to the memories. And the second item is the collaborations of the workers. So we need to make sure that the worker work together so that they actually do something which is more interesting than just the replication of the same work. And that involves synchronization of the distributed work. At some point, the workers will have to stop all at the same time to resynchronize their status and to share information, so communication of data between workers. Decomposition of work can involve operation decomposition, and that will be called task level parallelism. So you can have either multiple programs that do different things at the same time, or one program that is spawned multiple times, like I refer here, and it's called SPMD, single program multiple data, and that is the paradigm that you will see most in these sessions. As far as data decomposition is concerned, we refer to that as data level parallelism, and it can take multiple forms depending on the dimensionality of the data. You can chop the data or split the data in multiple ways. One very important way is domain decomposition, where you actually decompose the data based on the physics or the reality that is described by the data. That is for decomposition. For collaboration, there are multiple degrees to which collaboration can happen. It can be completely synchronous, meaning that every worker is running exactly the same instruction at the same time than the others. It can be completely what we call embarrassingly parallel. So some problems can be solved by simply running a large number of workers working independently. And in between, you have fine-grained or coarse-grained collaboration, and that the distinction between fine and coarse depends on basically how many times per unit of time do the worker have to collaborate and to synchronize or to exchange data. Talking about exchanging data, there are multiple patterns that can arise. Point-to-point refers to one worker giving data to another worker, but you see that there are collective operations as well that you would see mostly in the MPI section, where you can broadcast from one worker to the others. You can broadcast the same information, or you can scatter information from one worker to multiple workers, or gather, which is the opposite operation. And a very important thing is for the reduction, and you will see that in MPI and OpenMP, is the fact of gathering information and at the same time performing an operation to summarize that information. Whenever we talk about collaboration, synchronization, parallel computing, we ask ourselves, does it work? And the measure of how work is efficient is called the speed up. And so the speed up is basically the ratio between the time taken for serial operation by the time taken by the same operation but in parallel. So basically, if you have something, a program that takes 1 hour, and if you give it 10 CPUs, the speed up is 1 hour divided by the time it takes with the 10 CPUs. If everything is perfect, you should see a decrease tenfold in the time it takes in parallel compared to the time it takes in series, but it's not always the case. And the ratio, when it's not perfect, is called the efficiency. So basically, it's the speed up divided by the number of processors. And if you create a graph like this, where you have number of processors and speed up, this is the linear speed up, which is basically the holy grail that we want to achieve. But most of the time, you will see something that goes like this. This is a typical success. You see that having a good efficiency is often easier with a small number of processors, but as the number of processors grows large, you will see that the efficiency often drops. The reason for that can be multiple-fold, but one of the reasons is often that not all parts of the code can be parallelized. So if you have a program that is depicted by these rectangles here, and this orange part is the part that cannot be parallelized, and this green part is the part that can be parallelized. So the fact that some part can be or some parts cannot be parallelized depends on the nature of the problem. Some computations can be parallelized, others cannot. And so you see that if you use 2 CPUs to solve the same problem, this part which is not parallelized would take the same amount of time, but this one that can be parallelized, you see that the length here is divided by 2. And if you add one more CPU, you see that this part will shrink, but this one will never shrink. So no matter how many CPUs you add to the resources, because of that part which is unshrinkable, you will not get a perfect speedup. Another challenge is the parallel overhead. This is a core graph of this program, and this little program just issues a hello world in parallel on multiple nodes. And in this whole core graph, maybe only this part is related to the fact of writing to the screen something. All the other functions are called are just there to make sure that the parallel software can synchronize, can exchange data, and can actually start on multiple nodes. So there's a lot of overhead when you start a program that needs to distribute its work across multiple nodes. And a third challenge that needs to be addressed when working with multiple computers at the same time is the load imbalance. You realize that if you need to stop the work and distribute it to the workers, if some workers don't do anything, it does not help for parallelization. But sometimes the way the data or the problem is constructed prevents you from perfectly distributing in a balanced way the task to the workers, and you can end up in situations like this where all these red rectangles here are just lost time that make the efficiency to work. Do you have any questions about those? I just opened a dictionary and read some definitions to you, but it will become more concrete in a few slides. Okay, so now I will talk about the parallel hardware, a hardware that we can use for parallel computing. But to show what I want to show, I need first to explain what the abstraction behind a computer is. So this is called the von Neumann architecture, and basically what you see is that there's a central processing unit. I'm sure you've heard the term CPU before. That has a control unit with the circuitry to organize the instruction, and the ALU, the arithmetic and logic unit here. And this unit is talking to the memory unit, where you have the short-term memory or volatile memory, and you have some inputs and some outputs, and this is the basic block diagram of a computer. Well, nowadays, a actual computer has a block diagram which is a bit more complex, but what you can see already is that there are multiple ALUs here. You see one here, one here, one here. So actually inside what is a single thread CPU, something that is not advertised to work in parallel, you already have multiple ports that are organized by a scheduler. And this is called ILP, so instruction level parallelism. And both the compiler and the CPU at runtime try to run as many instructions in parallel as possible. But as a programmer or as a user of the software, you don't need to worry about that. Another thing you see here is these blocks, which appears to be a bit larger than the others, and they are called SIMD blocks, so SIMD, single instruction multiple data. And these blocks are actually able to perform in one clock cycle multiple operations on different data. So if you have an addition or a multiplication, or a fused addition and multiplication, these units are able to do that on 4 or 8 or even more sometimes scalars at the same time. This is a very important thing to realize, and even though you should not really try to optimize the way they work, you should realize that they are there, and there are hints you can give the compiler to make sure the compiler uses them the best it can. So this is at the core level, so the single allocation unit you can get on a cluster. But the cores are always grouped multiple times into a chip. So when you go to the store, you want to buy a CPU. This is what it will look like. And inside this, you have multiple cores. So the cores is what you saw in the previous slides. So if you have one chip here, you can do what we call multi-core parallelism. And on a typical board, on a typical computer like this, you have already multiple sockets, so multiple processors. There are basically two ways of organizing processors and memory on a board, called either symmetric multiprocessing or non-uniform memory allocation. And there are two ways to organize the data, the way data can travel from one core to another. I will not go into further details about that, but oftentimes on large machines with a large number of processors per node, you will be talked about NUMA and NUMA placement, because you will have to think inside a node just a bit as if there were multiple nodes on the same machine. And then in a node, what you can have also are accelerators. So typically nowadays, GPUs that are specific hardware like this that you can add to a compute node to increase its computation power. Now, one node is nice, but the nicest thing is to have multiple nodes. And so if you have access to a cluster in a data center, you see that this is a collection of nodes. So typically every row here is a node, and you see the back here. And most important thing when we are talking about multiple nodes, so inter-node parallelism, is the network, because the data has to travel from one node to another node to the network. And so typically you will do that on if the cluster you are working on is equipped with a fast network. So as I said, at the CECI, this is what we offer. So clusters, you know that there are clusters on each site of the CECI universities. And they all look like the picture before. But it's not the only way you can work with multiple nodes in parallel. The other big framework is the cloud computing. So I'm sure you've heard about Microsoft Azure or AWS. Basically, behind the scenes, the hardware is the same. If I show you a picture of a data center, you will not be able to say whether it offers a cloud or a cluster. But basically, this offers virtual machines, while the cluster offers slots with slow. And if you group together multiple clusters from multiple sites, you can have a grid, like the grid organized for the CERN experiments, where data produced by the LHC is distributed over the world to multiple clusters where they do some physics. I don't know the details, you can ask Olivier for the details. But basically, this is called a grid. So multiple clusters of you having multiple computers, and each computer has multiple CPUs, and each CPU has multiple cores. And you see that there are different levels at which parallelization can occur. And maybe just to be complete, you've heard about SETI at home. So people who are looking for extraterrestrial intelligence out there. So the idea here is a bit like in a grid, but people are distributing software on all the computers of people who participate in the project. And they offer compute cycles from laptops or workstation or even larger cluster. And they are all organized to try to find non-random data in data from space. The same projects have been created for protein folding, something like that.
It was fold at home.
Fold at home, yeah, but it was protein folding.
It was during the COVID crisis, yes.
So here again, it's a different way of working in parallel by using regular computers, regular laptops all over the world. Any question about this? So you see, there are multiple ways we can think in parallel on even one CPU, then in one compute node that can have an accelerator, cannot. Sometimes you can have multiple nodes in the same data center, or multiple data centers hosting multiple clusters. So now the big question is how we try to extract power from those hardware. And the main question is this one: is parallelization automatic? The bad answer, the bad news is that, of course, it's not, except at the ILP level. So as I mentioned earlier, the fact that a single core can already organize work at some degree in parallel, this is mostly the CPU scheduler that does it, and also guided by the compiler. And you, as a user or as a programmer, you don't have to take care about that. As far as the SIMD instructions, so the other part in the CPU that can work in parallel is concerned, most of the time you don't have to worry about it. The compiler will do it, but the way you write your code can have an impact on the compiler and can lead the compiler to use or not use the SIMD chips on the chipsets. And you can use pragmas to guide or to give hints to the compiler so that he can use them the most. As far as intranode parallelism is concerned, it can be automatic if the library or the program you are using has been designed for it. So someone has to do the job. It might not be you if you are using Scalapack or another MKL library for mathematical operations that has been written by other people. Most of the time they will be written in a parallel way. But even then, you will need to be aware of that fact, and you will need to make sure that the environment holds the correct variables to make sure that the library or the program that you are using is aware of the multiple CPUs that it has access to. And you will have to make sure that the CPUs are using. As far as GPUs are concerned, it's the same thing. Either you are using a library or a program such as TensorFlow that uses GPUs in a transparent way, or you will have to organize it by yourself. But most importantly, you will need to make sure that the environment holds the correct variables so that your program is aware that there are GPUs available. These variable code-eligible devices is taken care of by Slurm for you automatically, so you don't have to worry about it. It's not the case for the non-threads variables by default. Some sites organize it for you, some others don't, so you need to make sure that something is done so that these variables are correctly defined. And for internode parallelism, there is never an automatic way to make it work. So even if you are just a user and not a programmer, you will need to make sure that the program is explicitly started on multiple nodes. And so you need to be aware of the network capabilities to make sure that if you are on a cluster that has only a very slow network, you should not try to do multiple node parallelism. But it will never be automatic. So if you have a job that works on a single node and then you want it to be faster and use multiple nodes, it's not enough to just add in your Slurm script -- nodes equal 2 or 4. It will not change anything if you don't make the effort of doing the work, distributing the work with typically MPI, as you will see later this morning and this afternoon. So this is the main message of this talk is that it will not be magic. It will not happen automatically. So you will have to add work in it so it works. Because it's something we often see, people who have program that runs on one core in one node, and then they add more cores or they add more nodes without thinking more about it. And they are expecting the job to go faster. And most of the time it's not the case. And they ask us why. And we have to go dig deeper with them. What is the program doing, how it's working in parallel, or maybe sometimes it's not possible to have some programs work in parallel. It's something that you need to think about. There are multiple paradigms for working in parallel. The two most common are task farming and SPMD. So in task farming, you have a master program that distributes work to workers, sometimes called leader-follower, or you can have no leader and the workers that still work that has to be done. So there is a pool of work to be done and the workers go fetch a piece of work. This typically involves no collaboration, and we are in the case that we refer to as embarrassingly parallel in the beginning of the session. SPMD, so it's a paradigm where actually a single program is containing both the logic for the distribution of the work and the logic for the computation. And multiple instances of the same program are started and connected together in a way, and this is the paradigm that you would see in MPI. And each instance is given an index so that it knows which ranks it has among the others. There are other parallel programming paradigms like MPMD, which is multiple program, multiple data. The same idea as SPMD, except that you can have multiple executables. Something that you most often see in climate science, where they have a executable that takes care of the input-outputs, another one that takes care of the modeling of the ice, another one that takes care of the modeling of the air, and maybe the modeling of the ocean, and they link them together, but they have multiple programs. Another paradigm is pipelining, which is the same idea that happens in factories when you build a car and someone takes care of the chassis, and then someone takes care of the electronics, and then someone takes care of the furnitures and so on. And divide and conquer is more a less used paradigm where the idea is to add resources at need. So an example is speculative parallelism. So if you have a structure like this in your code where you have an if statement that involves an expression that has a very long time to compute, normally what you do is you wait for the result of this before you can decide whether to do A or B. And actually with speculative parallelism, what you do is that you add more CPUs to do both A and B at the same time. And then as soon as you have the answer for this expression, you just drop the branch that you don't need. And it's a way to go faster, but the set of resources that you need evolves over time. And that is what we refer to as to divide and conquer. So these are the paradigms, the way we can organize the work. But in practice, what you need is a model. So a programming model is a library or a set of compilers features that allow you to write a program that actually starts the work in parallel. And you see here, really mostly a shopping list of libraries or tools that are available for you to work with. In italics are the tools that will be the topics of next sessions, like OpenMP here, MPI here. So if you work only on a single computer, you can use pthreads or OpenMP, thread building blocks, OpenCL to write programs that use multiple cores or multiple CPUs on the same core, on the same node to work in parallel. If you are working with GPUs, there are even more possible solutions here. We will be talking, well, actually, Orion and Olivier will be talking about CUDA, about OpenACC, if I'm not mistaken, maybe some others here.
If you talk about CUDA, you talk about HIP.
Okay.
It's exactly the same.
So HIP is CUDA, but for non-CUDA machines, basically. Multi-computer models involve for clusters message spacing. So PVM is what I learned when I was a student in computer science a long time ago, but it's been completely replaced with the MPI, which is nowadays the standard for message passing on compute clusters. Also, you can have PGAS, so partition global address space, which is a way to work as if multiple nodes that physically have distinct memories at a single memory. From a purely programming point of view, you will see the sum of the memories of the compute nodes as one memory, and behind the scene there will be the work necessary to organize the transfer that will be transparent for you. If you work on the cloud, you will mostly not use MPI, but rather either MapReduce or use the RDD from Spark. And if you work with the distributed computing, remember City at Home or Fold at Home, the software that organizes the work and that you need to use to create software that will run on this infrastructure is called VoIC. Do you have any questions about that? No? Basically, it's just a matter of setting the vocabulary so that the next sessions will give you the details. But now I would like to show you some tools that are available on any Linux machine. I will first talk about parallel tools and then about job control and parallel processes in Bash. So Bash, the shell that you have when you connect to the computer, already has some constructs and methods for working in parallel. And then I will show you some tools that are already available in any Linux distribution. And I will talk a bit about GNU Parallel, which is a software that was developed in the framework of the GNU program. And that, as the name implies, serves at working in parallel. So first, I want just to make sure that you realize that for not every, but most of the tools that you use in your everyday work on the Linux machine have a parallel counterpart. So if you are used to using gzip to compress some files, maybe compress tar file, gzip is working purely in series, but actually if you install pixi and use pixi instead of gzip, you move from using a single core, single thread program to using a multi-threaded program. And just by using the correct tool, you can make your process faster. Also, Grab is purely serial in the typical implementation that you will find on your Linux machine. But you can install a small program that does exactly the same called RibGrab. There are others like egg or AG. But these programs are able to work in parallel, and they will use all the cores that you allow them to use on the machines that you're working. Sort, by default, is equipped with the parallel option. So if you have a very large file to sort, don't hesitate to use -- parallel, and you can specify the number of CPUs you want to use. It's built in, so it would be a shame not to use it. And SCP or BC, they all have parallel counterparts. So if you are doing something that you feel is taking a long time, and you think that the program that is doing it is a bit old, you can look for a more recent version of the program that works in parallel. So now I will move on to bash process and bash jobs, and I will show here a little example that I will carry on for the rest of the talk. This is a bash program that does something useless, but it takes 1 second to do it, and it's for illustration purposes. What it does is it takes an input file with 1 letter per line, and then it creates an output file, or it writes at the standard output the same letter, but with the other case. So here, if we, the idea is that we feed it with capital letters and we get lowercase letters. So that's why it's called lower. Okay, you see the idea, and every line here is processed by taking 1 second. So it will allow us to measure time and see what is happening. So here what you see is I run the lower program on a file called d1.txt, and I'm creating a file called r1.txt, and I do that again on d1 to produce d2. Well, I could have put another file here. So in bash here, because I separated the commands with a semicolon, bash will run the first one and then wait for the first one to stop, to finish, to complete, and then it will start the second one. To illustrate that, I will measure the time with the time command, and for time, to measure the whole time of this whole set of operations, I need to enclose them in curly braces. Okay, so if I do that, simply I have 3 lines here. Basically, we'll only focus on the first one here, which is the time allocated to the user. And you see it has taken 8 seconds. Okay, I forgot to mention that these files have 4 lines in them. And so each run of the lower program takes 4 seconds. And if I have 2 times program to run, and I have the semicolon in between, you see that it takes 8 seconds. Okay, you understand the long line here? If we replace the semicolons with the ampersand, and it's something you have briefly learned at the bash session earlier this year. If you replace this semicolon by an ampersand and this one other by an ampersand, bash will start the second run as soon as it has started the first one, not as soon as it has finished. So bash will not wait for the first one to finish. It will start the first one, put it, as we call it, in the background, so that the second one can start. But if you write it like this, without this wait here, the time will only measure the time it takes to start, not the time to completion. What the wait here does is make sure that the curly braces here is not reached before both here are finished. So if we do that, you see that the output is a bit different, because every process that is sent to the background can write to the console, but not only once. It's organized into jobs. You see 1 and 2 are 2 job IDs, so you should not be confused with, you should not think of those as job IDs in a Slurm context. So these are also called job IDs, but it's in the bash context. And you see that the total time was 4 seconds. So this and this have been running in parallel, and the total time to solution was halved in 2. So with this ampersand, you can actually create parallel for loops in bash this way. So this is a typical for loop in bash with 2 commands to run. And what you do here is enclose the 2 commands into parentheses. So it's a bit different than before. Here we are using parentheses to actually create what we call a subshell, and you end the subshell with the ampersand here. So again, every iteration in the loop would go in the background, and we add wait at the end, so that the next operation here does not start before all the loop is finished. Okay, so this is a typical construct to create a powerful loop in bash. Any question about that? So this is basic bash, but you need to be aware of the ampersand and how the ampersand works to work in parallel. Now, in a Linux cluster or Linux machine, you will see some nice tools, and I will talk here about Xargs. What Xargs does is take something from the input, from the standard input, and start a program with that something as an argument for that program. So to be more concrete, I'm in a directory where I have 4 files that also have 4 lines, the same file as before. So if I run ls d question mark, which is a placeholder for a glob for 1 character, .txt, you see that I have these 4 files. If I write something like this, like I take the output of ls, and with the pipe, I give it as an input to the standard input of Xargs. -n1 means to work line by line, only 1 line time, and echo file. And then what will happen is this command is run as many times as we have lines here, with these outputs being appended here by Xargs. Okay, it's a bit confusing maybe at first to understand how it works or how Xargs works, but this is simply what is given as input is added as command line on the command that is started by Xargs. Okay, one nice feature of Xargs is the -P here. So you see that if I measure time here, I have 4 files. I run them. I run the lower program on each file, so it takes 16 seconds. Now, with the same command line, with a little difference here, which is a -P4, I'm asking Xargs to spawn or to create 4 processes at the same time. So actually, the 4 instances of lower will be started at the same time. And you see that the total running time is fallen back to 4 seconds. Okay, so this is logically equivalent to writing this, except that you don't have to write it explicitly. You just list the files and use Xargs to give each file as an argument to the lower command. And if you write with -P, it's equivalent to having the commands separated with ampersands and having a wait at the end. Okay, so whenever you have a large number of files to process in parallel, rather than writing a for loop and then having to think about how I can make this loop run in parallel, you can use Xargs and -P to make the processing go in parallel. Because something that I did not mention with the path for loop is that in the structure that we've seen in the previous file, there is nothing to control the number of CPUs or number of processes that are started at the same time. So if I have a loop that goes from 1 to 10, it will start 10 instances at the same time. And maybe you only have access to 2 CPUs, and then you will create contention. It's not what you want. Here, if you have access to only 2 CPUs, you put the 2 here, and Xargs takes care of everything for you. So here, this is the case where we one program and many files. You can have the other way around with several programs and one file. So here what you see is just like before, I'm running the lower program on an input file called d.txt with 4 lines in it. And I create a tmp.txt file. And you see that this tmp.txt file is used as an input to another command, which is called here upper. And I'm sure you can infer that it does the opposite operation. And then it produces a final result press. So here, written like this, because the commands here are separated with a semicolon, you see that it takes 8 seconds, which is what we expect. The nice thing is that in Bash and Linux, you can create special files called FIFO, first in, first out, FIFO, with this mk-FIFO command here. So I created a file in advance, and this file will be all temporary files to which the first program writes and from which the second program reads. And now if you see that if I use the special file here, and I use the ampersand here, actually what happens is that as soon as this one has written a line here, this one is able to read it. So their processing can overlap. And so the result is that instead of taking 8 seconds, it takes 5 seconds. There's a 1 second penalty in a sense, because this one can only start after this one has produced something, and that takes 1 second. So after 1 second, this one has produced something and this one can start. So the total computation time, provided that you have access to 2 CPUs or 2 cores, is 5 seconds. So this is if you have several programs that you need to chain in a way and a single file. But you can also have one program and one very large file. So assume that you have a very large file and each line in the file needs to be processed independently. This is something you can do with the split command. Again, it's a command that is available on any Linux distribution. So here you see exactly as before. I have a d.txt with 4 lines and I feed it to lower. Here I feed it to the standard input, but it works the same. And here in the example, rather than feeding the whole file, I first split it. And you see here the data number is r divided by 4, meaning that I will split the file into 4 different pieces. And then I will run the lower program on each of the pieces. And you see that in the end, it takes 1 second rather than the 4 seconds that were expected if you simply run like this. Here, what you see is I run exactly the same line as here, but I run the top command to see which processes are available. And you see that there are 4 instances of the lower program that are running at the same time, which can explain why it took 1 second rather than 4 seconds. So we have seen multiple files in one program. We've seen multiple programs in one file. We've seen one program in one large file. And the last option is to have several programs and many files. And here I'm suggesting that you get interested into the make files. So I'm sure that if you have already needed to compile programs on a cluster, you have faced a make file and you have learned that make files are designed to create software from source code to binaries. But actually, make files have been designed to do whatever needs to be done when you have files and programs to run on files. So here is a typical make file where I define what are called targets here, which are 4 result files. And then I define rules. And each rule says that, for instance, the something.res file is created from the something from tmt file with the upper command. So the syntax is not nice to read, but once you've learned it, you know how it works. And this rule says that the something.tmp file is created from the something.txt file with the lower command. Having defined this and having the files in the directory, you can run make, and you see that it will run all the programs that on all the files need to run, and it takes 32 seconds. And if you count the number of times a line is processed in the whole setup, you will realize that 32 seconds is the correct, the expected amount of time. Now, the nice thing about make is that just like Xargs, make has an option to run in parallel. So because we define the dependencies between the files and the programs, make is able to find the processes and the sequences that it can start in parallel. And so just by running make and then -J4, you see that the order of the operations is a bit different. Here, it was processing file by file. So it was creating d1.res from d1.tmt. But here you see that it first created all the intermediate files and then ran the program to create all the end files. So the total running time has been divided by 4, just because we were able to add the -J option here. So we've seen in those slides how to deal with very large file with one program. You can split it with several programs. You can use FIFO, so the type of files which has a specificity that you can write and read at the same time in it. You can do the same with pipes, so Linux pipes. If your program is designed to read or write to standard input and standard input, you can do the same thing, same chaining and pipelining with pipes rather than with FIFO files. And if you have many files to process, you can use Xargs if you have only one file, one program that needs to process all the files, or you can use make to use multiple programs on multiple files. And the nice thing to remember is -J for make or -B for Xargs will automatically use multiple CPUs to process the files. Any question about this? It was a bit fast, but you have here a catalog of tools and you can refer to them. The slides are not already on Indico, but they will be by the end of the day. So you can always refer to them to see which case you are in and see which program you need to use. And they are all very easy to use and of course, well documented. So as long as you know which program to use for which case, which is summarized here, you will be able to do what you need, whatever you need to do. I will take 4 more minutes to talk about GNU Parallel because it's something that is not always installed everywhere on every cluster, but it's a very nice little tool. This is a screenshot of the website. It's part of the GNU project, so it's been there for a long time and it will stay for a long time. The way it works is a bit peculiar, but it works. So here you see Parallel, so it's the name of the command. I have here a program that I want to run. Here, for the sake of the demo, I'm using the echo command. And you see here 3 times a column, so 3 columns. And then you see here a list, 1, 2, 3, 4. And what Parallel will do is run this command on each of the items in the list. Okay. So here you see the exact same thing, but rather than having an explicit list, I'm using a bash curly braces expansion. So this is pure bash, nothing to do with Parallel, but you can use the same tips that you can use in bash in Parallel, of course. And you see here, it simply echoes from 1 to 10. Here, replacing echo with sleep, I show you that it works in Parallel because it takes 11 seconds rather than 1 + 2 + 3, so on. And again, here you see that here I'm using bash globbing in the list, and with echo, it will simply list the files in the directory. Okay, of course, there's no point in listing files in Parallel, but you will see that we use that concept later on. The nice thing about Parallel is that it can use place orders. So whenever you have elements in the list, you've seen in the previous examples that actually the elements in the list are used as parameter for the command, but it's placed at the end of the command line. But here with the curly braces, they act as a placeholder. So with writing echo and then curly braces, every curly braces will be replaced with an element from this implicit list. And the nice thing is that the curly braces can have some specific syntax attached to them to modify the element. So here, with the dot inside, it will remove any part of the string that is the right part after a dot. And then with dot press, it will replace with dot press. So by writing this, I will actually do write the first element of the list, and then the first element with a .txt written by replaced by .rest, and so on for the rest. With this syntax, you will actually drop the path of a file and only keep the last part of the file. So if you write this, it will expand to this, and if you put a slash here inside the placeholder, the content of the placeholder will be simplified to this. And these are some techniques to manipulate the file names or manipulate the numbers that you are working with in a way that is easy to do with GNU Parallel. You can have multiple lists, always separated by those 3 columns. And if you have this, GNU Parallel will create all pairwise combinations for you, and it will echo this. Okay, so it's another nice thing. If you have typically a parameter set to sweep and another parameter set, and you need to create all pairwise combinations, rather than writing by yourself a 2-level for loop, you can just use Parallel. If you don't need all pairwise combinations, but this first one combined with the first one here, we just use --x apply, and it will only create the pairwise combinations index by index. As I said earlier, the placeholders here, they can actually refer to elements from this list or this list. So curly braces with a 1 here refer to the element from the first list, and as you understand, the curly brace with the 2 here refers to elements in the second list here. A nice thing also is that you can store the list in a file like this, rather than writing it in the command line, in which case, rather than having 3 columns, you would have 4 columns. But sometimes I hope they will stop adding columns, but the 4 columns here, you are actually asking Parallel to read this file. With these, you tell him that a file is a CSV file that has 2 columns. And you see that Parallel is clever enough to recognize the headings of the columns. And so here, this placeholder will be replaced with the element from the first column here. And this placeholder will be replaced with the element from the second column here. So if you have a set of experiments to run with multiple values for multiple parameters, you can put them all in a CSV file, for instance, and use a construct like this to start your program with all the different set of parameters. GNU Parallel also has nice options to work with a file. So if you remember the split example I showed earlier, GNU Parallel is also able to split a large file in multiple chunks and feed those chunks to a program that is started in Parallel. You can specify the number of jobs to run in Parallel with -j, just like in the case of the makefile. And then you can use -s to connect to remote servers with the SSH. So actually, if you have access to multiple workstations, you can use a construct like this. The first time you run GNU Parallel, you will see something that a message from the author asking you to cite this paper whenever you produce results with this software. So the talk is reaching the end, but I can suggest, if you are willing to discover more about GNU Parallel, is to try to reproduce all the examples from the previous slides with split, with xargs, with make, and with the FIFO with GNU Parallel. And here are the solutions. But I will conclude now. So I've been showing you very quickly the bird's view of the field of parallel computing from hardware at the instruction level, at the core level, at the node level, at the cluster level, and at the word level. I have given you a short list of programming models. Some of them will be delved into details by Orion and Olivier afterwards. And then I have shown you some tools that you can already use without writing any parallel program to start working in parallel using the bash commands and using the GNU Parallel. Do you have any questions from me? Yes?
What's the difference between write, ask, and what?
Okay, so I will start with a job. So a job is a set of operations that you want to treat as a single and distinct unit. So you get to decide what a job is. So a job could be to run program on some files or to run program to create files. And so typically a job is described by a submission script that you submit to a scheduler so that the job starts on one or multiple nodes. And inside the job, you can have multiple tasks. And a task is what Slurm will consider to be a unit of work that can start in parallel. So inside a job, you can have 10 tasks that start in parallel doing some stuff. And you will see in the MPI session that comes afterwards that you will try to think of a task as a process in MPI. And every task will be actually an MPI process that do something and works with other tasks. So all the tasks are started at the same time. And then within a task, which is basically an instance of a program, you can have multiple threads, which are in a software context, multiple flows of operations that can run concurrently or in parallel. So basically, when you write a program, you write instruction 1, then instruction 2, and instruction 3, and this is a thread. But you can also say, okay, this is a thread, but I also have these set of operations or instructions that I want you to consider as another thread that will start possibly in parallel. And there you will be interested in the OpenMP session, where you will see how threads can be created from C code or Fortran code. But the best way to understand is to write software that does all this.